All right, now that we know how to handle the Laplace transform of a derivative, let's come back to this differential equation and see what the Laplace transform does to it. So if we hit both sides of this equation with the Laplace transform and use the linearity property of the Laplace transform, we get Laplace transform of y double prime plus 3 times Laplace transform of y prime plus 2 times the Laplace transform of y equals Laplace transform of 1. Okay, now Laplace transform of y double prime, we know what this is now. That's what we worked out in the last video. So this is s squared times Laplace transform of y plus minus, and then the power on s goes down by 1, and the number of derivatives goes up by 1. So Laplace transform sort of counts as the minus first derivative in this context. So up by 1 means the 0th derivative, so initial value of the 0th derivative of y. And then minus the power of s goes down by 1, so now it's s to the 0, so 1. And then the number of derivatives goes up by 1, so y prime of 0. Okay, so this is all Laplace transform of y double prime plus 3 times Laplace transform of y prime, Laplace transform of y prime, which is s Laplace transform of y minus y of 0 plus 2 times Laplace transform of y equals, and on the right-hand side, Laplace transform of 1, that's one that we know. That's 1 over s. Okay, now looking at everything that shows up here, there's only one term in this, there's only one Laplace transform in this whole thing, and it's the Laplace transform of y. So what we can do is gather all of the Laplace transform of y terms on the left-hand side. So this term is going to stay on the left-hand side, this term is going to be on the left-hand side, this term is going to be on the left-hand side. And all of the terms that don't have the Laplace transform of y, we can move them to the right-hand side. And then these two terms also to the right-hand side. Everything on the left will have the Laplace transform of y in it, so we can just factor out that Laplace transform of y. So let's see, we have an s squared right here. This term is gone, this term is gone. We have a 3s, and then plus 2. And then on the right-hand side, we have 1 over s plus all of these terms coming from the left-hand side that have initial conditions. So s times y of 0 minus y of 0, s times y of 0 plus y prime of 0 plus 3 times y of 0. Okay. And then finally, it looks like we can solve for the Laplace transform of y just algebraically. So we get 1 over s, so I'm taking this first term here and just putting this quadratic in its denominator, so 1 over s times s squared plus 3s plus 2 plus, and then all these terms with initial conditions, s times y of 0 plus y prime of 0 plus 3y of 0 all over s squared plus 3s plus 2. All right. So we have this equation, equation that tells us what the Laplace transform of y is. But so we found the Laplace transform of y, but remember we were actually hoping to find what y is. The whole point is to try to solve the differential equation. So we aren't quite done here because we don't know what y is yet. what we really need is some way to undo the Laplace transform. What we need is an inverse Laplace transform. But how do we do that? I mean, we have a lot of formulas that tell us Laplace transforms, but if you think about it, each one of those formulas for Laplace transform are really also a formula for an inverse transform. So this is the notation that we're going to use for the inverse Laplace transform. So if you write down some formulas for Laplace transforms, so for example, we found that the Laplace transform of 1 is 1 over s, you can turn this into a formula for an inverse transform. This says that the inverse transform of 1 over s is 1. Similarly, the Laplace transform of t to the n is n factorial over s to the n plus 1. You can turn this into an inverse Laplace transform formula. The inverse Laplace transform of n factorial over s to the n plus 1 is t to the n. Now you might think that it would be a great coincidence if you ever saw n factorial over s to the n plus 1, but remember, since the Laplace transform is linear, the inverse transform is also linear, and that means we can move this n factorial outside of the inverse transform and then divide both sides by it. So we could write this as inverse transform of 1 over s to the n plus 1 is equal to 1 over n factorial times t to the n. Right, so maybe one last example, the Laplace transform of sine of at, we found it was a over s squared plus a squared. And that means the inverse transform of a over s squared plus a squared is sine of at. So if we go back to our differential equation that we were trying to solve, this one, what we need to do now is take the Laplace transform on both sides of this equation, and the trick is going to be figuring out how do we write this, all of this stuff inside of our inverse Laplace transform, how do we express it in a way where we can use our inverse transform formulas? Right now it looks like there might be no way that we can do that, but if you look carefully at this rational expression, it's 1 over s times s squared plus 3s plus 2. That's s plus 2 times s plus 1. Okay. For this term with all the initial conditions, let's just suppose, just for the time being, that all our initial conditions are 0, just so that we don't have to deal with this extra term over here, although we'll see that it works out similarly to the first part. So if we want to take the Laplace transform of inverse Laplace transform of 1 over s times s plus 2 times s plus 1, so this is going to be equal to y, if only we can calculate what this inverse transform is. But one of our Laplace transform formulas is that the Laplace transform of e to the at is 1 over s minus a. So a rational expression like this, as long as it has a linear denominator, we could take the inverse Laplace transform of it. Well, this denominator isn't linear, but since it's a product of linear factors, we can use partial fractions decomposition to write this as a sum of simpler rational expressions. So if we compute the partial fractions decomposition here, we get some number that we'll have to work out, some constant, over s plus some other constant over s plus 2 plus some other constant over s plus 1. Okay, so whoops. So let's see if we can work out what those constants are going to be. So there's a really nice shortcut for calculating these coefficients in this product of linear factors case for partial fractions. It's called the cover-up method. And if you haven't heard of the cover-up method, you should definitely look it up because it makes, usually from partial fractions, you get some big linear system of equations that you have to solve for A, B, and C. But the cover-up method makes it so that you can actually do this one case with a product of the linear factors basically in your head. So let's see, if we do the cover-up method, I think for A we're going to get 1 over 2. For B we're going to get plus 2. And for C, we get minus 1. So you can double check me on that. But whatever these coefficients turn out to be, right, we need to take the inverse Laplace transform. But remember, the inverse Laplace transform is linear. So we can move our constant multiples outside, distribute the inverse Laplace transform. So we get 1/2 inverse Laplace transform of 1 over s plus 2 times inverse Laplace transform of 1 over s plus 2 minus 1 times the inverse Laplace transform of 1 over s plus 1. Okay, and all of these inverse Laplace transforms are ones that we know. So to get the inverse Laplace transform of 1 over s, we need to think of a function of t whose Laplace transform is 1 over s, but that's 1. Okay, plus 2 times. Now for the second one, we need to think of a function of t whose Laplace transform is 1 over s plus 2, and that's e to the minus 2t minus, and now we need to think of a function of t whose Laplace transform is 1 over s plus 1, and that's e to the minus t. All right, so you can see that we've solved the differential equation. Actually, it was an initial value problem because remember, along the way, I added the initial conditions that y of 0 and y prime of 0 be 0. So we solved this initial value problem just using the Laplace transform. So we started with an IVP, an initial value problem, and we want to find a solution. And the direct route, right, sometimes it's too hard or impossible, but the idea with the Laplace transform is you take the Laplace transform, and what you get when you take the Laplace transform is an algebraic equation for the Laplace transform of y. Since it's an algebraic equation, you can solve the equation with algebra instead of solving a differential equation. So when you solve this algebraic equation, you get you find the Laplace transform of y, and then you undo the Laplace transform using the inverse Laplace transform, and you end up with a solution to your initial value problem. So this is our general outline of how we can use the Laplace transform to solve differential equations, But what we should do before we dive into some examples of actually solving differential equations this way is look at some more examples of finding inverse Laplace transforms, because there are a few tricks of the trade for writing the sorts of things that come out of solving this equation, writing it in a way that lets you take its inverse transform.